Hello, Algebra 2 folks, and welcome to Graphing Exponential Growth and Decay Models. You need your graphs that I gave you in class, a calculator, and a pencil. So if I were to ask you these two questions, one, would you rather have $10,000 given to you every day for the next 30 days, or option B, a penny a day, but it doubles every day for the next 30 days? Which one would you take? I bet most of you would take option A, $10,000 a day every day for the next 30 days. So let's look at their tables and see if that makes a difference. So by day 9, I've got $90,000. Okay, here's a penny a day, but I'm going to double it every day for 30 days. By day 9, I have 512 pennies? 512 pennies. That's only $5.12. That doesn't look good at all. Now what would you do if I told you that the amount at the end of option B was 737,418? Now, which one would you take? Because I'm pretty sure that after day 30 of $10,000 a day every day for 30 days, you're only going to make $300,000. So which one would you rather have, 10 million or 300,000? And I'm hoping you're going to take 10 million. All right, so here we go. That is what we call exponential growth. It starts out really slowly, barely moving, and when we get closer to day 30, we're going to get $10 million. I mean, we're way up there. So it starts out slowly and then grows really fast. So that's what we're going to talk about today, exponential growth and decay. All right, I need you to write this down because these are a couple of examples of what exponential growth and decay really are. Exponential growth and decay are things that grow or decline, but they grow and decline by a certain rate. So bank account interest, that's going to be a growth because you put money in your bank account, you make interest, you make money. Population, Bismarck's population is growing. You can also have declining population, so maybe some small towns around North Dakota are losing population. Radiation, that's a decline. Depreciation of your car, the value of your car, the minute you drive it off the lot, it has lost a lot of value. And carbon content in fossils, using carbon dating, that's how they decide how old mummies are. And that's a decay. So those are just some ideas of what growth and decay really are. These are two graphs. One graph represents a growth graph, and one graph represents a decay graph. This would be the growth graph. This would be the decay graph. Growth means you start out slowly and you gain a lot really fast. This says you start out with a higher number and you lose it pretty fast. Okay, so that's the difference between a growth and a decay graph. All right, the goals for today, you will be able to graph exponential growth graphs and decay graphs. You will be able to identify the domain and the range, and we are going to learn about this new word called asymptotes. We're going to learn how to identify them on your graph. Okay, so graphing, domain and range, and asymptotes is what we're learning today. So this is the exponential model for a graph. Okay, y equals a times b to the x power. Now the x is in the exponent. That's why we call it exponential graph. B is the base. Okay, so if you have a growth model, your b is going to be greater than 1. If you have a decay model, your b is going to be between 0 and 1. Now, if it's greater than 1, we call that a growth factor because it's going to grow by that factor. If we use decay and it's less than 1 but greater than 0, we call that a decay factor. Okay, so those are the two options that we have. We either have a growth or a decay. Now let's go ahead and graph this function. Okay, let's go ahead and graph this. First of all, if you see something like this, we always want to put our base that has the exponent in parentheses. So this is the base of 2. Now, that's greater than 1. Therefore, this would be a growth graph, okay? Now, when I am plugging numbers into here, we want to know what kind of values we can put into the x. Well, we always talk about domain, and what values can we use for x? So, do you see a division sign? Nope. So we don't have any problems with dividing by 0. Do you see a square root sign? Nope. So we're not going to have any trouble with negatives, all right? So we are going to use the values -2, -1, 0, 1, and 2, and that is going to be our domain, all reals. Okay? Now we're just going to plug this into our calculator. 3 times parentheses 2 to the power of -2. That is going to give us 0.75. -1 will give us 1.5. 0 will give us 3. 1 will give us 6, and 2 will give us 12. So -2, 0.75, 1, 1.5, -1, 0, 3, 1, 6, and 212 is off my chart. Now here's my graph. Nice curve shape. We got to have the curve shape going on. This is a growth graph. It starts out slowly, and then it's getting bigger faster. Now, my question to you is, what value is this going to keep going and approaching? Well, here's the deal. If you put -10 in there, you're going to get 0.0029. Well, that is really close to 0. Did it reach 0? Nope, it's pretty close, but it's still not reaching 0. What if we put a -100 in there? What are we going to get? Oh my gosh, when I stuck a -100 in there, I got something to the power of 30. That means 30 zeros. Still not 0, but close to 0. So this graph, basically what it's doing is it's approaching 0. It's never going to touch 0, but it's going to get closer and closer and closer to 0. Now, if you think about that, if you don't have any money in your bank account, can you make interest off of it? Probably not. Not if your bank account is 0, you're not going to make any money off of it. So the range is greater than 0, which means the asymptote is y equals 0. So that means we are going to approach this asymptote, but we're never going to touch y equals 0. Okay, so that's the first graph. So now I've mentioned the word asymptote, and you're probably thinking, what is an asymptote? Okay, so an asymptote is a line that the graph approaches more and more closely, but it never, ever touches it. So if I'm looking at this graph, I can tell that this is a growth graph, okay? Because it's starting out slowly, and then it gets big fast. Okay, so here we go. So this is a growth graph because it's growing, okay? Now, what value is this approaching? Well, it's approaching 3. It's never going to touch 3, so the asymptote is y equals 3. Okay, so the domain of this function would be all reals. The asymptote is y equals 3, and so then the range would be y is greater than 3. All right, let's try a couple more examples. So now I have my 2 here, and I have a different exponent. So I got a little bit more things in my exponent. It's still exponential. And it's growth because our b is greater than 1. So this is still a growth graph. Okay. Let's talk about some shifting that's happening here. This shifting is moving it down 5. Well, guess what that means? The asymptote that originally was at 0 is now moving down 5. So now I can just go ahead and put my asymptote at 5. Y equals 5. My domain is still going to be all reals. Okay. And now I'm going to plug in values, because I can plug any values I want in here because it's all reals, from -2 to 2. But here's the problem. If I plug in -2 to 2, I am going to see a straight line. I am not going to see very good points here. And in order for you to have a growth graph, you need to see that curve. And so if I do -2 to 2, I'm not going to see that curve. So what I need to do is I need to think about the shifting that's happening with the x's. So the shifting that's happening with the x's is that I'm going right 3. So if I'm going to typically use -2 to 2, I would shift all of them right 3. And if I'm going to shift them all right 3, I'm going to add 3 to all of those original values and use those values. So I'm going to do 1, 2, 3, 4, and 5 is what I'm going to use. So when I plug in a 1, I'm going to plug in 2 in parentheses. I'm going to do my caret, and then I'm going to do 1 minus 3 in parentheses. These got to be in parentheses. Subtract 5. And when I do that, I get -4.75. Okay, and when I plug in a 2, I get -4.5. And when I plug in a 3, I get a -4. And when I plug in a 4, I get a -3. And when I plug in a 5, I get a -1. Now, hopefully that's enough to see that curve. If I don't see that curve, I need to put some more values into this table. So 1, -475, about right there. 2, -4.5. 3, -4. 4, -3, and 5, -1. Okay, that's enough for me to see that I have a curve happening. And remember, my graph cannot touch that asymptote. So, and my values are greater than that number. So, oops, my asymptote should be y equals -5. I forgot that negative there. I'm sorry. So y equals -5 is the asymptote. I'm sorry. And then y is greater than -5. Okay. So I apologize that I didn't put the -5 there, but the asymptote is down 5. This always tells me my asymptote, okay? So if my asymptote is down 5, my y would be y equals -5. All right, so let's do one more problem and see how that goes. So now I have f of x equals 1/5 to the power of x plus 1. And I'm looking at the base, and the base is less than 1. It's less than 1, but greater than 0. That means I'm going to have a decay graph, okay? And so with my decay graph, I can think of this the same way as a growth. It's just going to look a little bit differently. It's going to start high and go low instead of starting low and going high. All right, so this tells me my asymptote. So I should already know that y equals +1. And I said it right this time. I'm sorry about last time. Okay, my domain is all reals, just like everything. I don't have any shifting on my x, so if I don't have any shifting there, I can just go ahead and use -2 to 2. Can go ahead and plug that into my calculator. 1/5 in parentheses to the power of -2 plus 1, and I will get 26. Then -1 gives me 6, 0 gives me 2, 1 gives me 1.2, and 2 gives me 1.4. And as these numbers get higher here, if I put a 3, a 4, a 5, 100 in here, it would never touch 1, but it'd get awfully close. It might be 1.0 with 30 zeros, but it'll never touch 1. So I'm not going to plot the -226. -1, 6 I'm going to put on there. 0, 2, 1, 1.2, and 2 really close to 1. I see the curve. It's going to approach that, but it's never going to touch it. So it's y is greater than 1, not greater than or equal to, but greater than 1. And that's it. So that's decay graphs. All right. Now let's classify the exponential models by just looking at the equations. So if I look at these equations, what am I looking for? To identify if it's growth or decay, I have to look at the base. So this is my base, 1.2. Is that greater than 1 or less than 1? It's greater than 1, it's growth. 0.3, greater than 1 or less than 1? Less than 1, decay. Now remember, it has to be between 0 and 1. Your base can never, ever, ever be negative. 3/5. Yep. That is decay. 7/2. Oh, I got you, didn't I? Because it's a fraction, so you're thinking it's decay, but 7/2 is 3.5. That's actually growth. So be careful with those. Not all fractions are between 0 and 1. All right, so we have been able to graph exponential growth and decay models, identify domain and range, talked about that word asymptote and what it means, and how to classify them. Hopefully you took good notes, and that is all, folks, and we will see you later.